Good evening, everyone. Welcome back to this 14-week webinar series on quantum algorithms using Qniverse. Last intermediate session, we had with us Dr. Naresh, who went through the qubits, gates, which are the building blocks of quantum computing. This week, we are thrilled to feature Professor Anirban Pathak, who will be presenting an insightful session on quantum veto protocol. Professor Anirban Pathak is a renowned theoretical physicist with expertise in quantum optics and quantum information, particularly in the areas of quantum cryptography and photonic quantum computing. He earned his PhD from Vishwabharati University, Shantiniketan, and currently he is the professor and head of the Department of Physics at Jaypee Institute of Information Technology, Noida. He has active research collaborations with groups in India and abroad. He has made significant scholarly contributions, authoring numerous book chapters and publishing extensively in reputed scientific journals. His research has been supported through completed and ongoing projects funded by DST, MAITI, DRDO, and Indo-US collaborative programs. Over the course of his academic career, he has supervised many PhD scholars and mentored a large number of postdoctoral research. Uh, with this, we welcome you, sir. Over to you, sir, now.
Thank you for the introduction, and I would also like to thank Dr. Henry for considering me for this talk. So we share a very strong relation with CDAC in different ways, and some of the slides I'll show and as a top header, which is from CDAC cake lectures I delivered few months ago. But anyway, this Veto is a very interesting protocol, and let's slowly move to that. And it's nice to know that in the introduction you told that in the last week somebody already introduced quantum gates, but I kept few slides for basic, considering that there may be some people who were not in the last week but in this week. So I tried to make the presentation complete in sense that even if someone is attending this series of lecture for the first time, then one can follow. So let me share the screen first. Okay, so let me start with the formal part of it. So as the title suggests, Quantum Veto Protocol. So now CDAC has a very nice simulator in which they have implemented a quantum veto protocol. So I'll talk primarily about that, but I'll slightly speak about another implementation called socialist millionaire problem. So all these belong to a family of problem called secure multi-party computation. But quantum veto is a specific case of a particular kind of voting, and there is some success of implementing voting. In the left hand, I show success of ID Quantic in implementing or a kind of voting scheme for municipal election in Geneva, where the postal ballots were secured by quantum cryptography. So some relation of quantum and voting was established, and very early, about 15 years back. Then many people wrote several protocols of quantum voting. I also wrote a couple of protocols on quantum voting. But then voting involves multiple people. The number of voters are very large. And at the moment, the technology, the equipment available are not of that quality that you can maintain so many voters. But normally the veto happens in UN. UN is the most popular example of where veto is implemented, but there are very few permanent member of United Nations Security Council. So number of countries giving veto are less. And with the present technology, it is impossible to implement veto. So I'll move to veto with a very nice quote from a paper and a line from Star Wars movies. But before that, I just want to tell the participants that in case you wish, you take a screenshot or note my phone number and email. So if you have any questions afterwards, even if you can of course ask at this webinar, but even if after that you have some questions, you can drop me a mail or a WhatsApp message, and I will try to address. So this is where I am located. So this is Noida, and this is Jaypee Institute of Information Technology. And somewhere in the building shown in bottom right, I have a lab, and in the lab we do quantum cryptography primarily, but it's a photonic lab. And now CDAC is also a CDAC Bangalore is also a collaborator with CDAC Bangalore, IISc, and SETS Chennai. We are supposed to work on a project on photonic quantum computing. So everything we do involves photons, optics, and there is an aspect of security. So normally it is seen that cryptography and computing is different. The problems in which the cryptographic idea and computation comes together is secure multi-party computation. And one such nice example is Veto, in which, so our lab has both cryptography and computing, both are photonic. And Veto is a very nice example where these two merge. But before we move to Veto, there is an interesting paper by Howe and Peter, and this paper starts very unconventional way. So this paper starts from a catch line in a galaxy far, far away. And if you are those who are of my age, means who are familiar with the series of films called Star Wars, and they used to start with this line. So I have shown in the right, a long time ago in a galaxy far, far away. So in this they are starting with, during an open meeting, the Galactic Security Council must decide whether to invade an enemy planet. One delegate wishes to veto the measure, but worries that such a move might jeopardize the relations with some other member states. How can he veto the proposal without revealing his identity? So the answer is then veto must be anonymous. So we are interested in anonymous veto, where it will not be disclosed that who is giving veto, who is executing the veto right. And that's needed in many situations, but it's a nice way, unconventional way in which a paper starts showcasing the need of anonymous veto. And when you do anonymous veto using quantum resources, it will be called quantum anonymous veto. So where we need, so just like the Galactic Security Council, we have UN Security Councils where permanent members hold veto power. So it's not yet anonymous, but if for a certain reason it needs to be anonymous, then quantum anonymous veto will work. In important cases, there may be a set of judges or juries, and often you see that the decision happens with that three people agree, one people disagree, but it's come in media that one who has disagreed, but it can be on veto. So there are situations where there are important decision has to be taken by a set of juries, and they don't want to disclose that who vetoed a particular decision. So these are the cases where, these are only example cases. There may be many other cases where, and there is some advantage. So what, just like the previous quotation shows that he does not want to jeopardize the relation with other countries or other galaxies. So similarly, it's anonymity protects individual rights. It protects individual from potential negative consequences for expressing their views. So if somebody is not very familiar with veto, so veto allows finally to come at a decision in which everybody agrees. So it's not a majority voting. In this kind of voting, if anybody disagrees, suppose there is a proposal. So at my home, I tell that today we want to eat Chinese. And if any family member disagree, it will not be Chinese. So only that menu will be decided in which everybody agrees. So everybody has it will not be a majority voting. Say three people want Chinese and one person want dosa. So we cannot go for Chinese. Even one person disagree on Chinese, we have to drop that. But then if it is happening publicly, we may be angry on him. So anonymity helps to protect individuals' rights, creates a window for honest feedback. So individuals can express dissenting opinions without the fear of being marginalized. So if your identity is not known, then you cannot be marginalized. Protects interest of minority. If majority wants something that may not be correct, so it may be an investment decision a company is making. A few wise people want that this will not be a right investment, so it can stop the majority's view. So overall, it's actually a kind of voting. And all these things are part of a bigger picture called secure multi-party computation. So normally we call this task SMC, So the idea of SMC is that all the users give some input. So A give input I, B give a input J, C give a input K, and somebody computes f of I, J, K. But that person, whoever is computing, will only know that much information that can be concluded from the computation of the function I, J, K, but he will not know the value of I, J, and K. So there is a secure aspect, multiple parties involved, and there is a computational aspect because finally you are computing a function. So I'll show some simple examples to elaborate it. So this is where the tricks of cryptography and tricks of computing merges. And one such nice example is voting. So what happens in voting? Everybody votes. We want that who voted whom, that must remain secure. But at the end, I have to count the vote also. A particular kind of voting, there are many different kind of voting. And for computer scientists, or there are many classification of voting. So for example, the easiest voting is binary voting, where you are just saying yes, no. And then the voting is classified also as traveling ballot versus distributed ballot. So traveling ballot is easier. So the kind of voting in which we are involved are actually technically they are traveling ballot, that we all are going to a machine in which we are giving a vote. So in this essentially in the same ballot we all are putting our vote. So ballot travels to me or I go and reach the ballot is technically same for a physicist. But when there is you are choosing say a winner of Star Jalsa or voice of GTV or something like that, each of your mobile phone is working like a ballot paper. So that's called distributed ballot voting. But we are interested about a specific kind of voting called anonymous veto. So what will happen here? That if there are 5 voters, we are interested that if there is a proposal that 5 of them agree on that or not. So suppose there is a proposal, just like I was talking about the Chinese, suppose government put a proposal that India will host Olympic in say 2036 or something. But they need that all the ministries involved in the organization, they must agree. So all this ministry can put a veto. Eh, if any ministry disagree, then will not host Olympic. So there can be many such example you can construct. But if there are 6 people or 8 people have right to vote, one disagree, then that. But here you will see that whatever we are going to do is actually a traveling ballot kind of voting. So voting, anonymous veto, all this involves computing task. There is a security aspect. So they are taking the flavor of cryptography from where the security is coming and then finally computing. So they belong to a family called secure multi-party computation. A very special type of secure multi-party computation is voting, and a special type of voting is anonymous veto. But it does not mean the capability of voting implies that your algorithm can do anonymous voto, or capability of doing any secure multi-party computation task enables you to do voting. It's not like that. So voting is a special type of secure multi-party computation, and anonymous veto is a special type of veto. So I mentioned that when you do anonymous veto and you use quantum resources, it's called quantum anonymous veto. Normally we write it like QAV. So voting is very closely connected. Another problem which is very closely connected is called Dining cryptographer's problem. So those who are familiar with the classical aspects of AVNet, they know that these are Dining cryptographer's problem. And essentially what we do in the classical version, we actually compute XOR of different values, I, XOR J, XOR K. And so that makes it closer to quantum summation. And again, quantum summation is very close to another secure multi-party computation, which is called quantum auction. So there are very closely linked things, and anonymous veto, summation, quantum auction, quantum voting, and the links are in general sense are open for you to explore. So the way we defined in the previous slide is like basic definition. Anonymous veto is a mechanism where a decision can be made by a group without revealing which specific member, if any, voted against it. So there is a proposal at my home that there will be Chinese, and somebody said that I don't want Chinese, but we will not know who has voted against the Chinese food tonight. So, but how we write it mathematically? So an AV or anonymous veto protocol of n voters returns Vn is equal to 0. So Vn, look at the equation 1. I'll write only one equation. So in equation 1, that Vn is the finally I'm computing. It is 0 if Wi is equal to 0 for all I. So it means Wi is equal to 0. So Wi is the opinion of the ith voter. So if all the vote, so when a particular voter gives 1, that means she or he is performing veto. So if nobody opposes the proposal, nobody applies veto, then nobody applies 1, and then the final result will be 0. So if final result Vn after taking input from everybody is 0, then we say that nobody has applied veto. But if it is 1, otherwise, means whenever it is 1, one or more people have applied veto. So we need to compute this kind of function. But then, so finally it's a computation task, but because I'm calculating a function, but it involves security because I have to secure the identity of the person who has performed the veto. So that has a cryptographic aspects too. Now, what are the things needed? So first, eligibility. So just like in UN Council, Security Council, only certain nations can vote. So if they are not in front, then you have to authenticate who is voting. So no one except authorized voters shall be allowed to vote. And that's true for any voting scheme. So that's called eligibility. So how will you establish eligibility? So traditionally, even when you are doing cryptography, Alice and Bob needs to establish that they can talk to each other. So that Alice is really talking with Bob and Bob is really talking with Alice. So this we call identity authentication. Usually the protocols implement classical identity authentication. However, there are some protocols of quantum identity authentication. So along with my recently graduated PhD student Arindam Datto, I have also written a couple of proposals, but they are not also fully quantum. But why I'm mentioning spending time here, when I'll show this how we implement quantum veto using Qniverse, there will show that these are essentially proof of principle experiment. I had implemented it in IBM. That was also proof of principle experiment because you are not checking identity authentication of, or you are not doing eavesdropping checking. So then after eligibility, we have to ensure privacy. It means that nobody except the voter should be able to know how a particular voter has voted. So that's true for any voting scheme. Binding, no one, including the voter himself, can change the vote after its submission. So this is called binding. Then there is correctness. So if the adversary is passive, there is no if. So in the implementation of Qniverse, which will show there is no if at the moment, we are working in an ideal condition. So if the adversary is passive, then the result Vn is equal to 0 for all Wi is equal to 0 for all I. That's what the function I have shown in the previous slide is generated. In other words, it means that after faithfully following the protocol, one is able to successfully detect a veto has been implemented or not. Verifiability, all the participants can verify the final result. So if somebody has vetoed and the final result shows that there is no veto, then they will be able to disagree. Robustness, so this is specifically important for quantum implementations because there is noise, there is decoherence. So if the adversary is passive, then it should work properly because of the just there is no adversary, and just because of the noise, if my 0 become 1 or 1 becomes 0, then the protocol will not work. So we have to check in presence of different kind of noise. That's what we have done in case of IBM implementation, that in different kind of noise also it works. Now, I already mentioned that there is a bigger problem called secure multi-party computation, and veto is a special part of that. So to extend that, I'm just asking a simple idea that what is one-sided two-party computation. So it's not multi-party, it's two-party. So suppose there is Alice and Bob, and Alice has an input 1, 2, 3, n, and Bob has an input j 1, 2, 3, n, and somebody else is computing f of ij, but in such a way that at the end of the protocol, Bob learns f of ij, Alice learns nothing about j or f of ij, Bob knows nothing about I, more than what logically follows from the value. So I made an incorrect statement in between. I told that somebody else is computing f of ij, but this is one-sided two-party computation. So there are only two parties. So Bob is computing f of ij. So Bob will not blow the value of I. Bob's input is J, so Bob knows J. Bob will know Fij, but Alice will not know J. And Bob knows nothing about I. More than that logically follows from J. But now you can make it multiple party. That multiple parties are giving I, J, K, M, L. So their input, and one of the party is computing the function of I, J, K, L, M. But he or she will know only whatever can be obtained from that. So a very nice problem, which is also implemented in Qniverse, is called socialist millionaire problem. So the idea is that there are two socialists, two millionaire. They want to compare their assets. Say Alice is a millionaire, Bob is a millionaire, and they want to compute that they have equal amount of assets or not. So depending upon the assets, they keep on inputting this I and J, and I have to compute a function f of ij. If I is equal to j, it is 1, and if I is not equal to j, it is 0. So, or the opposite. So then we are essentially doing a quantum private comparison. We are comparing I and j. If I and j is equal to equal, then both the millionaire have equal asset. If not, they have different amount of assets, but we don't know whether it is equal or not. So this protocol, this is called socialist millionaire problem. So there are many such problems. The simplest problems are bit commitment, remote coin tossing, oblivious transform. When cryptography, quantum cryptography came, QKD came, people thought that cryptography will enable us to solve, quantum cryptography will enable us to solve all such problems. But you can easily understand that every problem cannot be solved in two-party scenario, and Low has a Low and Chow has a very interesting result, which I'm showing in the screen. But you think of a remote coin tossing problem. So Alice and Bob are separated, and Alice is tossing a coin, and they don't want to see each other. So if Alice tells that the outcome is head, Bob will say that that was my bet. If Bob tells the bet first that my bet is head, Alice will tell, oh, the outcome was tail. So now, how they can do it? So classically, the way it is done, Alice tosses the coin, puts it in a box, sends the box to Bob, but keeps the key with herself. After receiving the box, Bob sends the bet. After receiving the bet, Alice sends the key. But now here is an assumption that Bob cannot break the box and see the bet when the box reaches him. So if it is a digital lock, it's on its computational power. If it is a physical lock, it's in muscle power of Bob. We are making some condition. So that's why it's not unconditionally secure. But now when QKD comes, suppose you implement BB84 protocol, but if you implement in a two-party scenario between Alice and Bob, then Bob already knows the key. So here the BB84 will not help. So in two-party scenario, this kind of multi-party computations are not doable. So often we do it for three tripartite scenario. So socialist millionaire problem, I have already hinted. So what is the task? You have to compute f of ij is equal to 1 if I is equal to j, and else f of ij is equal to 0. So, and then there can be other comparison. So we have several protocols for that, but that's not the idea of today's talk. But you see that socialist millionaire problem is also implemented in Qniverse. Now, I mentioned that this is Veto is a special type of socialist millionaire problem, and then I mentioned that it's a special type of voting scheme. So I just want to introduce a very simple voting scheme. So this is Hillery's protocol, and it was published in 2006, and it is the first published protocol of veto. Sorry, voting, quantum voting, and it's very easy to follow. So instead of qubit, there are qdit, which are D-level system. So an honest, non-cheating authority, Charlie, prepares an entangled state, but entangled in qdit, say kk. So if there are 3 voters, I prepare 0 0 plus 1 1 plus 2 2. So it's a 3 level system. 0 is a level, 1 is a level, 2 is a level, and now there is a unitary. Anybody wants to vote yes. So this is a binary voting and distributed ballot. So the voting authority keeps the first qdit with herself and send the second qubit over the channel. So it went to the first voter. If he wants to give yes, then he apply a unitary that takes k to k plus 1. So 0 will become 1, 1 will become 2, and 2 will become 0. So my state will become 0 1 plus 1 0 plus, sorry, 0 1 plus 1 2 plus 2 0. Then it depends on how many voters said yes, and finally I do a measurement. So it will collapse to, say, only one voter has given yes, then it will collapse to 0 1 or 1 2 or 2 0. So from the outcome, I will be able to know that how many voters have voted yes. and check that whether majority have voted yes or not. So that's very, very simple protocol. But of course, implementation is difficult when the number of voter increases. But you see, one qubit is traveling from first voter to second, second to third. So this kind of voting has a name, technical name called traveling ballot. The ballot is traveling. So that is the case on what we have implemented in Qniverse. So background works. So I already mentioned in the previous slide also that we also have a protocol on quantum voting. And so that was, we wrote two protocols on quantum voting. One in Involve, we used a quantum assisted blockchain. The other one is more conventional unitary. Then comes our EPJ plus paper, Quantum Anonymous Veto, a set of new protocols. So this has partially inspired by a never published paper of Ramiz Rahman and Guru Prasad Kaur. So both of them work in ISI Kolkata. So they have a 2015 paper. So our voting idea and their unpublished paper, which is still in archive, was in background. And we find out the essential symmetry, and we wrote 7 protocols for quantum anonymous voting. So this EPJ plus paper reports 7 different protocols. So out of them, 2 protocols my former PhD student Satish implemented in IBM quantum computer, and one of those 2 papers is now implemented in Qniverse, and that I will explain. But I just want to mention this, that there are, if you are playing with Qniverse, you can play with the other protocols too and find out your own cases, implement them, check the impact of noise, compare that in presence of noise, which one is performing better, etc. So before I proceed, just in the beginning, I mentioned that if there are some new people in the audience or students in the audience, I just quickly introduce some of the basics. So normally we write a vector as, say, vector P as A I hat plus B J hat plus C K hat. So here I have written a vector A as A1 I hat. So what is I hat? I hat is a unit vector along X direction. J hat is a unit vector in Y direction, and K hat is a unit vector in Z direction. And what is this A1, A2, A3? They are the projection. So A1 is the projection along X axis, A2 is the projection along Y axis, A3 is the projection along Z axis. So this can be written as a matrix A1, A2, A3, because ultimately to describe this vector, I just need these 3 projections. So I could write it as a state column matrix. I can write it like a row matrix. I can write them like A1, A2, A3. What many way I can write. But the convention we use is this A1, A2, A3 as a column matrix. So that's what we use in quantum mechanics. Then what happens to the basis vector I hat? So I hat as a projection of 1 unit along X direction and nothing along YZ. So this becomes 1, 0, 0. Now, if we use a 2-dimension, then my basis vectors will be 1, 0 and 0, 1. So just keep this in mind. And then remember, this whole thing is called bracket. If you divide, the left-hand side will be called bra and the right-hand side is called kate. And that's the notation we use. So in this notation, now I'm working in 2-dimension and kate 0. So this, wherever my mouse is, so there is a line followed by bracket, a right angle. So this is called kate 0 and it's a column matrix 1, 0. So if we take transpose conjugate of it, so conjugate does not have much meaning here because it's all real, then I get bra 0. Inner product is just a dot product between these 2 matrices, and I can similarly write kate 1 as 0, 1. So this is the notation we always follow. So now, what is a qubit? Already it is done in the previous Wednesday's lecture. A qubit is a 2-level quantum system. So that you can visualize as a superposition of kate 0 and kate 1. And usually we write it like in general alpha kate 0 plus beta kate 1. But now we want to visualize a outer product. So already I have defined how to write a bra and how to write kate. So these slides are from my CAKES lectures given to CDAC, and the top of this slide has been prepared by the CDAC team. So anyway, so when you write kate A bra B, so this is called outer product. So inner product was a scalar quantity, a single number, but outer product will be a square matrix. So you can write that kate 0 bra 1, and you just multiply the matrix. Similarly, you can write kate 0 bra 1 plus kate 1 bra 0, and you see that there is a matrix, diagonal terms are 0 and the non-diagonal terms are 1. So this is simply a NOT gate. And you can easily visualize it as a NOT gate. So this is also a Pauli matrix X. So not operating on gate 0. So you can just write the entire matrix and see that 0 goes to 1 and 1 goes to 0. So this is the gate which will require in our quantum veto implementation. Will also require a Hadamard gate. So Hadamard is given by this kind of matrix, 1 by root 2, 1 by root 2, and minus 1 by root 2. So it takes 0 to 1 by root 2, 0 plus 1, and 1 to 1 by root 2, 0 minus 1. So I have shown explicitly all the matrix multiplication. And when we'll open the simulator, you will see that we are using this gate. So apart from Hadamard NOT gate, we have used control fetch, control C0 in Qinverse, and a JIIT gate, and some fractions of the JIIT gate. So JIIT gate is so these are called Pauli matrices. So X, Y, and Z, and identity is a simple identity matrix. So what JIIT gate does, it maps 0 to gate 0 to gate 0, nothing on 0, and changes 1 to minus 1. So then if you are starting with a state called, say, alpha gate 0 plus beta gate 1, Z gate will transform it into alpha gate 0 minus beta gate 1. So it's a fetch flip gate. It changes the relative phase between gate 0 and gate 1. Now, there is some kind of product. We have talked about inner product and outer product, something called tensor product. So what this tensor product does, so AB is a two-level system. So you can think it as a qubit. CD is another qubit. So you can visualize that as A gate 0 plus B gate 1, and the next one as C gate 0 plus D gate 1. But independent of that, the tensor product works in this way. If I have to do this AB matrix, tensor product CD matrix, A must be multiplied entirely with the CD matrix. So A times CD gives me ACAD, and B times CD gives me BCBD. So you see, scale inner product was giving me a number, outer product was giving me a square matrix, and this is giving a matrix, column matrix, but with a larger size. The dimension has increased. It's now 4 cross 1. So you can do specific cases which we have shown in the right. But then how we look at a circuit? So suppose I have a Hadamard gate and nothing in the first qubit line has a Hadamard gate, second qubit line has nothing. So then it's actually Hadamard is applying on gate 0, identity is applying on gate 0. So it's equivalent that Hadamard tensor identity is applied on 0 tensor 0. So we can do this. So I can write this Hadamard gate matrix, then the identity matrix. So 1 by root 2 will be multiplied with the entire identity, and that gives the first block of the rightmost matrix, then and so on. So it's a 4 cross 4 matrix, and when it operates on 0 0, you get the same thing. So in two ways we have to create the result, and you see that left hand side result and right hand side results are same. So we have to, and what it is 0 0 plus 1 0 by root 2, and you can see that since nothing happened in the second qubit, so impact of Hadamard is just creating a superposition in the first qubit. So these two qubits are separable, they are not entangled. Now how we create entangle? So we use a EPR circuit, or in the lab we use BBO crystal, etc. So when I say entangle, when I cannot write them as a product of two states. So when I can write them as a product of, say, 0 plus 1 by root 2 tensor product 0, it is separable. When I cannot write it like this state, 0 0 plus 1 1 by root 2, then it's called entangle. So this is very important, and entire discussion will be about 0 0 plus 1 1 by root 2 and 0 0 minus 1 1 by root 2. So there is a gate called C0 gate, which is also used here, and C0 gates map 0 0 to 0 0, 0 1 to 0 1, 1 0 to 1 1, and 1 1 to 1 2. So the first qubit is called control. So when the control qubit is 0, nothing happens to the target, and when the control qubit is 1, then the target flips, or not operations happens on target. But this is not the only control gate. You can think of a control JIIT gate. So what happened in control JIIT gate? If the first qubit is 0, then the JIIT gate will be applied on the second qubit. Sorry, if the first qubit is 1, then the JIIT gate will be applied on the second qubit. If the control qubit is 0, nothing will happen on the second qubit. So we can have any controlled unitary operations, but the most popular operation is C0. So continuing with that, so if you have this circuit in the right is called Hadamard circuit. Sorry, EPR circuit. So there is a Hadamard gate. So you start with 0 0. In the last slide, we have shown that it goes to 0 0 plus 1 0 by root 2. Now you apply a C0 gate. So what will happen? The 0 0 will go to 0 0. The first qubit is control. Nothing happens to the second. But in the second one, that 1 0, since the first qubit is 1, second qubit will change, 0 will flip to 1, and my state is 0 0 plus 1 1 by root 2. So this is how you can prepare a Bell state. And this, you can see that you cannot separate that what is the state of the first qubit and what is the state of the second qubit. You cannot write them like a tensor product. So this is entanglement. Now, in experimental realization of quantum anonymous veto, that is the paper with Satish, which has been implemented in Qniverse. So I'm coming to the protocol first, and then, so I have, as I mentioned, promised that everything needed for this lecture I will discuss in the beginning of the lecture. Now I'm describing a protocol in this part, and the next part will be to show that how this protocol has been implemented in a Qniverse protocol platform. So there is a semi-honest voting authority VA. So what VA does, VA creates a Bell state 0 0 plus 1 1 by root 2. So already in the previous slide I have shown that how you to create 0 0 plus 1 1 by root 2. A Hadamard followed by C naught will be enough to create 0 0 plus 1 1 by root 2. So here I wrote that check what C naught followed by Hadamard will do. So if you apply a C naught and a Hadamard, then this Bell states will map back. So like 0 0, so you will get back 0 0 because C naught and Hadamard is. So you can essentially transform a Bell state Bell measurement into computational basis measurement. So my protocol works in this way. So it starts with a start 0 0 plus 1 1, and Alice is the voting authority. She keeps the first qubit and or home qubit with herself, while send the second qubit travel qubit to the voter V1. And what V1 does, V1 applies a gate 1 0 is the first row, 0 e to the power I pi, and in the denominator 2 to the power t. So t refers to the iteration. So in the first iteration, so iteration numbers are value of t plus 1. So t is equal to 0 is in the first iteration. So what will be this gate? So then this gate is e to the power I pi 2 to the power 0, and 2 to the power 0 is 1. So it is e to the power I pi. And how much is e to the power I pi? In the right hand side we have written it's 100 minus 1. And if you go back, you can see that that is the Pauli's JIIT gate. So what JIIT gate does, it changes 0 to 0 and 1 to minus 1. So what I'm saying, that in the first iteration, a voter who wants to implement a veto implements a gate which is actually sigma JIIT. So then suppose you just assume that there are multiple voters, but only one voter has implemented veto. Then what will happen to this input state? So one qubit was with Alice, the other qubit is traveling, and if the second qubit is traveling and one voter has implemented, then 1 will become minus 1, the relative phase will change once and it will become 0 0 minus 1 1. So at the end, if Bob does a Bell measurement, Alice does a Bell measurement, she will know that one voter has implemented a fetch flip. Now what happens if two voters implement fetch flip, two voters implement veto? Then both are implementing a minus sign. Minus and minus will be plus, there will not be any change. So after one iteration, if you just apply, you can only identify whether the odd number of people have implemented veto or even number of people have implemented veto. So if odd number of people have implemented veto, so odd number of fetch flip will cause a total fetch flip minus, and then I'll be able to identify. But if even number of people implemented fetch flip or nobody has implemented fetch flip, then the state is same 0 0 plus 1 1. So I don't have any way after one iteration to identify whether, suppose I start with 4 voters, so whether 4 of them have implemented, 2 of them have implemented, or none of them have implemented. All such cases will give me 0 0 plus 1 1 by root 2. But if one person has implemented or 3% has performed veto, then there will be a minus sign and a Bell measurement will reveal that. So how to go ahead? So next time I'll implement VA performs a Bell measurement using the home qubit available with the travel qubit received from VN. Step 4, if I have a non-conclusive result, then I repeat A1 to A3 for t is equal to 1, then t is equal to 2, 3 is equal to 3, and so on. So just visualize what happens. So example 2, there are 2 voters only. So if there are 2 voters only, so first iteration, if one of them have put put a veto, then it will be 0, 0 plus minus 1, 1 by root 2, because only one voter, one fetch flip. So I missed a line here. And we can identify. But if both of them implemented veto, then it will be 0, 0 plus 1, 1 by root 2. Then I cannot identify. But now in the second iteration, we have the fetch factor I pi p2 to the power t, and this t is now 1. So this is pi by 2. So if none of them implement, the state will remain 0, 0 plus 1, 1. But two of them implemented, then each of them has implemented in the second iteration 1, 0, 0 e to the power I pi by 2. The product will be z gate. So because twice it is rotated by pi by 2, so resultant rotation is pi, and we have a state 0, 0 minus 1, 1 by root 2. The second iteration will be able to distinguish between whether one person has implemented or two person has implemented. Whether none of them implemented veto or both of them implemented veto. The first one will tell me whether the odd number of people implemented veto. I'm not interested whether one implemented veto or three implemented veto. We are interested whether veto is applied or not. So similarly, if you have 4 voters, if 1 or 3 perform veto in the first iteration, we'll get it. If 2 voters perform veto, after second iteration, we obtain the same thing. If 4 voters implemented veto, we have to go for the next one. Why next one? So next one is t is equal to 2. So e to the power I pi 2 to the square is 4. So each of them are implementing. So 4 of them are implementing e to the power I pi by 4. So 4 people are rotating by pi by 4. So at the end, it is a rotation by pi, and here a minus sign will come, and it will be a conclusive result. So this is the structure. So first, the VA prepares a bail state. So we have shown this circuit. Then the voting stage, all the voters, say there are 4 voters, they implement their identity or iterative phase operator, and then we have to do a bail measurement. So bail measurement can be mapped to computational basis measurement in 0-1 basis measurement. So just like from 0-0, I create a bail state, 0-1 creates another bail state, 1-0 creates another bail state, 1-1 create another bail state. If I put this C0 followed by Hadamard, then it prepares in the reverse order. So bail states will now be mapped to 0-0, 0-1, 1-0, 1-1, and this will transform a bail basis measurement into computational basis measurement. But in protocol, what we write as bail basis, this will be done. So that's the protocol. So we have started with initial state 5 plus number of veto 0, then the outcome is 0, 0, and looking at the outcome, you can find out that what happened, and I have already mentioned that. So now our task was, this webinar is about doing things with Qniverse. So how to do in Qniverse? So those who are new, you can go to qniverse.in and click first in the register, and once you register, then you click on this place where I'm saying that click here to login. So after login, this kind of things will come. Click on login, and you create with your, once you register, you give your ID, you create your ID and password of your choice, and when you log in, you will start with 150 credits. So I'll show my account. We have already used some credit, and of course you can go directly to Qniverse in/login and create your account. Once you are there, so this is, I'm showing stepwise manner how to go that. So click here first. So in this icon, when you click, and then you click select algorithm icon. So then, so initially you see this kind of picture, and in this picture you have all the gates on top. So this is a particular gate library called Clifford plus T. You can drag and draw your circuit. You can bring the Hadamard in your qubit line. So this Q0, Q1, Q2, etc. qubit line. C0, C1, C2 are the point where you will do a measurement, and the measurement outcome will be written on those classical lines. In the right hand side, there is a place where you can write directly a code, or once you have already written a circuit, you want to write a gate in between, you can write in the code also. And that's pretty similar to what you do in IBM or Qiskit. But if you are not familiar, you just do drag and draw, and see in the right hand side how your drag and draw operation is reflected in the code writing, and then very soon you will understand the symmetry and you will be able to write your code. But we are interested in a particular algorithm, so we clicked in this algorithm. Once we click this algorithm, this kind of menu comes. So on clicking on algorithm icon, you will see a window like this. So this has many algorithms: Dewey's algorithm, Dewey's-Chosar, Bhajirani, Simon's algorithm, Grover's algorithm, and you can play and learn each one by one. And then you can go down and find out Veto, or here is a search icon. In search, you just write Veto, and then quantum Veto algorithm will come, and you will have to click on load circuit. So once you do that, then you will see a circuit. So that's the step 7. So load circuit. But before that, you have to choose that for how many user you want to implement Veto. For one user, it does not make any sense. The minimum number of user allowed in Qniverse is 2, and maximum number which is implemented now is 8. So then you can choose. Say here I have chosen 4, and then we have to choose that who is applying Veto, because this is actually a simulating a situation. So you are choosing that, suppose player 2 or voter 2 has implemented Veto. So here is a V. You have a choice. I will show that, and then you make load. And depending upon the, so like you remember that I have already explained, if there are 2 voters only, then 2 iteration will be sufficient. But if there are 4 voters, I will need 3 iteration. So depending upon how many voters you have chosen, the number of iteration will change and the circuit will be repeated. So that is implemented in Qniverse in the background, and you will be able to see. So we have chosen, how much we have chosen? We have chosen 4, and we have chosen that the 4 voters. So we need 3 iteration. We have already explained, and second voter is implementing the Veto. So here you see the Veto implementation involves a phase gate. So here I start with Q2 starts with a 0, and there is a NOT gate. I have already explained a NOT gate. We have already explained Hadamard and C0. So if you look at the extreme left block, so Hadamard followed by C0. So what it is creating? It is creating 0, 0 plus 1, 1 by root 2, the Bell state. What this C0 followed by Hadamard is doing? It is doing nothing but doing a Bell measurement, but transforming Bell measurement into a computational basis measurement. What are written in between? The first gate after Bell state is identity. That means first voter is not implementing Veto. Second is control phase. So this voter is implementing Veto. So there is a phase gate, and what is deciding that it will implement? Here is a control gate, and you are making initial input as 0. So initial input is 0. So then NOT gate is making it 1, and when it is 1, then the phase gate is implemented. So here it is, a phase gate is implemented and Veto is implemented. So it continues in this way. So if this is conclusive, then the second and third circuit becomes immaterial, and finally the measurement will tell me that what has happened. But how many iterations? You can see that the similar circuit block has been applied 3 times. So this represents 3 iterations. So if you go for 8 users, then there will be 4 iterations, but we'll log in and see that. So let's play with Qniverse. So I want to, whatever I have explained, now I just want to log into my Qniverse and check that it works. So for example, one number of iteration readed is, minimum number of iteration readed is 1 plus log 2 base n. But you cannot make a circuit for 3.3 times. So if it is greater than 3, it will be 4. So for 2 users, you need 2 iteration. For 3 to 4 users, you need 3 iteration. For 5 to 8 users, you need 4 iteration. 9 to 16 users, you need 5 iteration. So we just want to check that it happens or not. Then what else we have learned? We have learned that the phase gate, which we implement to implement Veto, changes in every iteration. So we will check that that's happening in the Qniverse or not. So let's leave with the last slide. I'll come back to last slide. So this is my Qniverse account. So let's click on the login. I have already saved my password. So once I log in, as I described, you see this kind of screen. So I mentioned that you can drag and draw circuits, and if you drag and draw, you can see that, say I bring the Hadamard gate here, and then you see this code will change here. So if you bring another gate, say a Pauli matrix in the next qubit line, so immediately in the left, right, you see that Hadamard is written here in Q0 and Y gate is written in Q1. So now you learn the technique. So even if you don't know this programming language, that if you have to implement a JIIT gate in the third line, then you will write JIIT followed by Q within square bracket 2 and then a code. But anyway, what I mentioned that I have to click on this and then click on algorithms. So we click on algorithms and then several algorithm came. I'm interested in Veto. So I write Veto. So once the Veto come, we click on load circuit. So what I wanted to implement first, say 4 user, and the second person gives Veto. So let's change it. We have already shown a screenshot of that. Let's third person give Veto. So it's a Veto we choose. You can also play with me, and then we put load. So our circuit has come. So what we were expecting? So there is so Q2 is now in 0, and this plus is a NOT gate. It converts into 1. Then H followed by C0, we have already discussed that it will create a Bell state. Then first and second user never give Veto, so they are identity, and this person is giving Veto. So what is expected? In the first position, it will be a JIIT gate. So that's what we have discussed. So we check this gate. So we click on this, and then you see there are 4 icons are coming. So you click on, say, first in this third icon. So the third icon is showing you a gate. I'm just making it increasing, and you see that this is written like this is like pi by 1 by 2. So this is the equivalence will be a JIIT gate of this circuit. And to know it more, we do one more thing. So we click on CP again, and now I click on information. So in information, this is a control phase gate, and you see what is written. So this is 111 and e to the power I theta. So this theta is actually the phase which it is implementing, and in control manner. So only if the first qubit is 1, then the second this will work. Now the question is, we wanted to play and check that whether it in the second iteration. So this left hand side is first iteration. Apparently the circuit looks same, but when you will click, you will see that the phase is not same. So in the second iteration, the factor below pi should have been changed. So now you see it was pi by 1 by 2, and now it is pi by 2 by 2. So now in the third iteration, it should change again. So you check in the third iteration. So this is pi by 4. So initially it was 2 to the power 0, then 2 to the power 1, then 2 to the power 2. So as expected. So this is, you can run. How to run it? So to run the circuit, here in the extreme right, there is a button run. So it's taking some time. So I'm not running it. So and when you run a circuit, those outcomes will be in the circuit ID, etc. And then every time you run, you lose some of your credit. So for example, I started with 150 and now I have 120 or 125 credit. So I run these 5 jobs and at the cost of 5 credit each. Now let's do, I told you that we want to play with it and check. So load circuit again. So we change it from 2 to say 8. So I just want to, so what is my expectation? So now I give, instead of 1 person, so let's multiple persons give Veto. So I'm giving 3% to give Veto, and there are 8 voters. So what do you expect? So if there are 8 voters and 3% give Veto, so there will be 3 such control phase gate, and for 8 voter there will be how many iteration? There will be 4 iteration. So let's install the circuit and check that Qniverse works as per our theoretical expectation or not. So you see now 3 voters are implying Veto. So this is the first block. The structure is same. So my 4th, 5th, and 8th voter is giving every time the Veto, and rest are identity. Hadamard followed by C0 is creating Bell state. C0 followed by Hadamard is doing Bell measurement. And if you go from left to right, you will see the second iteration, third iteration, and here is a 4th iteration. So iteration follows the rule, and in short, it's working the way it is expected. So this is what I wanted to show you and explain Qniverse. And now we are almost at the end. And before I end, I once again repeat that you can play with Qniverse do socialist millionaire problem and other problems, as well as if you want to do, if you find that anonymous veto is interesting or voting is interesting, there are multiple protocols. One protocol has been given as example. So you can also design your own protocol and test, or you can test the existing protocols, and especially 7 protocols reported in our earlier papers, and implement noise also. So far what we have implemented, there is no noise. So I'll finish here. Almost my time is also over. It's 2-3 minutes. So before that, there is a couple of advertisement. So we have a national quantum mission project in which that involves CDAC Bangalore also. And I mentioned that we are supposed to build a photonic quantum computer together. And for that, we are looking for JRF and postdoc or RA. So if anybody is interested, and especially if you have some skill set in doing optical experiment, please apply. And our department offer MSc Physics with possible specialization in quantum technologies, and PhD in this area as well as different areas. But PhD is closed for this year, but MSc is still open. And finally, for the senior people, Professor C.M. Chandrasekhar, who is also our collaborator in this photonic quantum computer project, and myself, we are editing a special issue of Quantum Information Processing Journal, which is published by Springer Nature, called Quantum Information in India. And submission is open till 15th August. So if you have any interesting idea or already prepared a good manuscript which can represent quantum information activities in India, please submit your paper before 15th August. So thank you. I'll stop and I'll be happy to take questions.
Yeah, thank you, sir. We have a couple of questions. One person by name Guru Raja, he asked, how this QAB protocol withstand different quantum attacks?
Oh, security proof we have not discussed, but so the rigorous security proofs are present in our papers. But this one, only one weakness means all these protocols have, the here is semi-honest. So if any such protocol, so this kind of protocols, they are secure against the conventional attacks, but there is an assumption that VA who is implementing the veto is semi-honest. So what semi-honest means? Semi-honest means they follow the protocol honestly, but remaining within the protocol, they may try to cheat, they may try to, so IJK are the inputs, they may try to read IJK. But if they are semi-honest, these protocols are secure. And another problem with every secure multi-party computation problem, and even whether it's quantum, it is classical, if it involves n party and n minus 1 collude, then it will become insecure. So if out of 100, 99 people are dishonest, then the protocol will fail. But otherwise, these secure multi-computation protocols are secure.
Thank you, sir. Another question by Anayat Bashir. Why we use classical approach for explaining quantum veto for one-sided two-party problem, and what essence we get from its approach?
No. In cryptographic problem means all these problems had a classical counterpart. So for example, you are doing key distribution. So traditionally for any secure message, you need a key. So only when you use quantum resources, it become unconditionally secure. Before that, it was conditionally secure. So the problem is still there in the classical world, but the classical solutions are conditionally secure. They are based on assumption that certain problems are very difficult to solve. That depends on mathematical complexity. Whereas in quantum world, the security comes from no cloning, Heisenberg's uncertainty principle, collapse on measurement, such physical principle. So, but the problems, all these problems, dining cryptographers problems or socialist millionaire problem, they do exist in the classical, but the classical solutions based on complexity of the problems. So there is a family of problem in cryptography called post-Cold War problem. So socialist millionaire is one of them. So in essence means to achieve unconditional security, we are using this. So there are two kind of things. In computation, the quantum essentially gives me speed up and in cryptography, it essentially gives me unconditional security. And secure multi-party computations are such kind of things where the advantage of both the world merges. So that's why it's very interesting.
Okay. Thank you, sir. Sir, I have one my own question. Given this veto protocol ensures anonymity and tamper detection, can this be extended to our normal general election kind of a ballot voting system?
No. So actually, initially we wrote those kind of protocols. But then, when there are, that quantum states are very, they are not stable. So you prepare a state, it's there for 1 millisecond or so.
Okay.
So you cannot really do anything physical with them. But in the present situation, because if there is a election and there is a 1 million voter, so a qubit is going from one voter to other voter for 1 million times. That's a distant dream. But in principle, there are protocols. So I also showed a protocol, quantum Veto. So, but in voting also there are different kind of voting. Everywhere it's not majority voting. So there are rank kind of voting. So voting is a very interesting computational problem, and voting has many solutions. So and many works on voting. But yes, the answer is yes. There are protocols for voting, and it can be in principle, but the technology is no way close to implement that. But in anonymous veto, the problem is that what was when we started writing, we had UN Council is mine. So in UN Council, there are only 6 members, Security Council. So for 6 members, it's handling that, it's going applying 6 unitary. This is possible with the present. So like your implementation is also implementing 8 members. But if this 8 become 8 into 10 to the power 6, then it's not realistic, at least for near future.
Okay.
So I can see many questions in the chat.
Yes, that is what I am asking, sir.
Also, you
I'm,
are reading from the chat.
yeah, I am consolidating and I'm asking those questions.
Okay.
Santosh,
Yes.
Santosh, there is
Yes.
one interesting question from Vishal, which is not
Yes,
technical,
I was
but I
about
think
to
it will
ask
help.
the next question.
Yeah.
Sir, is there a PhD in quantum computing for working professionals at Jaypee Institute?
Yes, and this time also 2 people from CDAC has applied. But then the thing is that there is a UGC rule that one has to be within 200 kilometers. So for Bangalore, if we have to take somebody because there is a coursework and such thing, but this time 2 people from CDAC Noida has applied.
Okay.
So it's technically possible, but so one person is actually from CDAC Pune, but he is posted in MIT. And one person from CDAC Noida, which we have forwarded these applications. But for Bangalore people, it's difficult because its distance is more. So the solution is probably that to take a co-guide from. So if Chandru or somebody can be co-guide, then it is technically possible. But UGC rule says that you have to be within 200 kilometers.
Yeah. Otherwise, whoever are close to 200 proximity of Jaypee Institute, they can
That's
apply.
technically possible, but one has to come for coursework on Saturday for first year.
Yes. Okay. So one more question from Rehan Khan. Does the veto algorithm or any similar algorithm or combination be called as an alternative to blockchain technology? Can its
No,
application solve the large energy problem as in case of blockchain?
no. Actually, there is a blockchain also has a quantum analog, and we normally call it quantum assisted blockchain. And we have a protocol in which we have used quantum assisted blockchain for voting, but it's not other way around. That voting is not used for blockchain, but the blockchain is used for voting. So, and if you have interest, this is an interesting problem because literature is very small. So if you want to study voting, there means maybe 500 papers you have to read first to know that what has been done. But in as far as blockchain and quantum blockchain is concerned, there is a handful of paper, maybe maximum 10 papers are there. So knowing the whole literature is very easy, and doing something. But the thing is other way around, that blockchain is useful for voting, but not the quantum voting schemes or quantum veto scheme is used for blockchain.
Okay. Sir, one more question. What are the main security vulnerabilities in the quantum veto protocol if a subset of parties is dishonest or tries to learn other inputs? Are there known quantum solutions for malicious party detection?
Yes, means this. So I have already addressed this because I mentioned that this is vulnerable only when it's an n-party protocol and n-1 people call you.
Okay.
So if it is less than that, then it will not fail. It will be difficult.
Sir, the last question: how scalable are quantum AV protocols? Why AV protocols are only for private voting?
Only for
Private voting, or it's for like veto?
I don't. So no. Veto is not private voting. So in any voting, okay, if it is not private, if it is not anonymous, we are publicly doing. That's what is happening in event council. Then there is no cryptographic scheme. There is no need for cryptography. That can be in any case done. So you can do it and then you can fight with each other. So in the beginning, we told that may hamper the relations, means when or somebody's identity is disclosed. Suppose there is a very sensitive case in a court, and there are jury of 3 judges, and the conventional media is of particular opinion, and 2 judges is in favor of the opinion, and one is disagreeing, one is giving veto, and that's publicly disclosed. Then the judge and the judge's family can also be hampered.
Right.
But when it is anonymous veto, so and unless this anonymity is needed, there is no role of cryptography. So you can have a situation where anonymity is not required, then you don't implement cryptography. And as far as scalability is concerned, means we can implement means now this 5, 6, maybe 10, and even in the voting, the kind best protocols which are even proof of principle implementation, they are binary voting. So there are only two choice. The choice is between yes and no, like this or that, but not for our kind of ballot paper. That there are protocols, but they are very difficult to implement with the present technology there, and you cannot go beyond say 10, 15 users. Means if you have hundreds of users, you cannot implement, but in real voting there are millions of users.
Right. Yes. Yeah. Thank you, sir. Thank you very much. We have come to the end of this session. It was a very
So just
insightful.
once again, since I see there's many questions in the chat.
Yes.
So if I just request everybody, if your question is not answered in the first slide itself, I have shown my email ID and phone number. So you drop me a WhatsApp message or a mail, I'll answer all the questions. So
Yeah,
just note
that's
them. Even if you forgot to
kind of
note,
you.
then this lecture is probably in YouTube, so you can take my phone number and just drop me a message, because I see that many questions are.
Yeah, many questions are coming. Yes, that's true. Thank you very much, sir. So kind of you. It was a very insightful presentation on the Quantum Veto Protocol. It was a thought-provoking and glimpse into the future of secure and anonymous quantum decision making. With this, we have come to this uh, week 3 webinar session, and I thank all the participants for joining and listening to the professor's lecture. Few announcements. We will keep posting you the details of quiz over our GitHub and Zolit channels. Please attend those. And the record video session, we will post it on our YouTube video channel. Please do watch it. And while joining to the webinar, please join with your registered email address so that we mark your attendance. So that finally at the end of the series, we can see that who have attended, and we can give the certificate of participation. With this, thank you, Professor. Thank you very much for your kind cooperation and taking your time at a busy schedule. Thank you very much. And let's all meet next week. Thank you all.